Hello everyone, Ernest Heavyside here. Well, today I'm talking about space elevators. I saw something on Twitter and I was like, it kind of inspired me to start thinking about space elevators. So I was like, oh, I'll do a space elevator stream. It sounds fun. Like, the problem is simple enough. I mean, let's go through it. Sounds great. Yeah. So the thing about space elevators is, well, let's introduce the concept. Like, what is a space elevator? Alright, let's go to the other room. So, let's get my GIMP up. So a space elevator, let's draw a circle. So this is the Earth. This is the Earth. Okay, we're gonna color it in like green. We color it in like green. Come on, come on. Okay, there we go. So here is the Earth. Oh, I should have done blue. Anyway, so the distance of the gravitational, the strength of the gravitational field. Let's talk about that first. So it actually, within, let's say the Earth had a uniform density, right? Let's say the density of the Earth was just constant all the way through. It's not, of course. You know, it's a little bit more dense towards the center. But it's sort of a mathematical approximation that, you know, you can use when you're solving a homework problem in your physics class. So assuming that the density of the Earth is constant, so inside the Earth, if you start at the center, well, you're being pulled by the mass in the same direction, in the same force, all directions, right? So the mass over here is pulling you this way, mass over here pulling you this way, pulling you this way, and so you actually have no gravity in the center. It's like you're in the middle of space or something. You have no gravity. Which would be interesting, you know? That would be interesting. But anyway, as you move away from the center, your gravity actually, the force of gravity downward actually increases like here's a graph. Oh, I need to put this on a new layer. So here's a graph. And let's say that the y-axis here is like your force of gravity. So this is like F over here. This is like F over here. And then over here is like your radius from the center, right? So this is 2 axes to this graph. Well, what do you think it looks like? Like, as you get away from the center, what does this graph of force versus radius, what do you think it would look like? Well, it takes some calculus to prove this, but basically it goes up linearly, actually. Linearly, like this. And then, once you reach the circumference, once you reach the edge, it goes down. It starts dropping, and it goes down by a squared relation. So it's like a squared, you know, 1 over r squared. So that's what that looks like, and that is interesting. So we have the Earth here, and at a certain point, like, as you get away from the Earth, the force of gravity decreases, right? And also, one thing that increases is the time it takes to make a full circle around the Earth, right? Because the circumference gets bigger and bigger. So, like, if you're out here, you have a lot further to go around, because you have to go all the way around in a circle. So that increases with radius too. So there is an optimum point where you circle the Earth at the exact same rate that the Earth turns, and that is called the geostationary point. It's about 26,000 miles away from the Earth. And actually, why don't we go through the math and prove where the geostationary point is? You could probably do that. I mean, you won't get completely exact, but you might be able to get it somewhat exact, right? So if I were to go to my this is my latex here. So if I were to go to my window, this is the radius of the Earth. have it in kilometers, of course. It's nice to use metric units. Whenever you're doing like a scientific problem, you want to be using metric units because they convert very nicely. You don't always have to use them, of course, but whenever you're doing like a scientific problem, especially that involves like energy calculations and stuff like that, it's just nice to use metrics. So the radius of the Earth is, let's put it in our spreadsheet. Let's like copy and paste into our spreadsheet. So this is like a good way to do it. I have the spreadsheet here. Just go like radius of Earth, paste that in. Oh wait, no. Actually, a little trick that you can do is you can like paste it into a text editor first, and then copy and paste it into your spreadsheet, so it loses all of its formatting and stuff. That's kind of a nice trick that you can do. Oh, let's make it 12. Yeah, so here's the radius of the Earth in meters, not kilometers. I added 1,000 to get it in meters. Now, what is the mass of the Earth? Mass of the Earth? Here it is. It's huge. the Earth is very massive, you guys. Like, that's why gravity has an effect, because gravity is a very weak force, of course. Yeah, the Earth is massive. So going times 10 to the 24, right? Yeah. So how do I put this? I guess I could go like x10. Okay, spreadsheet. Okay, mass of the Earth. I'm gonna go like times 10 to the 24th. You should register this. Oh wait, no, I gotta do like equals. Oh man. Do I not know how to use this version of the text editor? I don't want to like play around with Windows all the time. But anyway, we can use these to hopefully calculate the point at which the speed that an object goes around the Earth balances with the Earth's rotation. Like, so it goes around in exactly 24 hours. Yeah, I was looking at Wikipedia before, and they're like begging for donations now, which is interesting. Oh, here we go. Okay, got it. There it is. Mass of the Earth is 5.97 times 10 to the 24th kilograms. And so we're like ants compared to the Earth, of course. And that's, wouldn't have it any other way. Okay, so now the force of gravity at the equator, like at the radius of the Earth. Well, let's use the acceleration of gravity, right? Accel of gravity at radius. So we can call that like A naught is going to be 9.81 meters per second squared. So using this, we could figure it out, right? So how would we do this? Well, we have the mass of the Earth, we have the radius of the Earth, we have the force of gravity at, oh, well, we need like G, like the gravitational constant. We could like look that up, I guess, if we wanted to. Gravitational constant. So the units for the gravitational constant are a little bit like weird. Okay, so it's 6.67430 times 10 to the negative 11th newtons times meter divided by kilogram. Yeah, it's just like the inverse units of. Okay, here it is. So yeah, this is a small number. So actually, how was this calculated? I believe it was originally calculated with the Cavendish experiment, right? That's an experiment that I myself actually did at one point. So the Cavendish experiment, you're actually using like, actually it might be here, right? If we search for it. Yeah, look, it says Cavendish, or the Cavendish gravitational constant. So, the 1798 experiment, the Cavendish experiment. So, basically you have like lead balls. Here it is. It's showing, yeah. You have like lead balls suspended from a foil, a very thin like foil of string. And that foil of string has a spring constant of like twisting, right? So a spring can have a constant of stretching and compression, but it also has a constant of twisting. So this is a very delicate arrangement. These steel balls are hanging from this very thin foil. And then you put other steel balls near them, right? Like really close to them. And it causes them to deflect. It causes the foil to deflect very slightly. And if you know the spring constant of the foil, then you can determine the exact force of gravity. Of course, you know, you have to get it to within orders of magnitude. But using that logic, you can get the gravitational constant. And you see, here it is, over here on the right. Over here. You have your torsion wire. And this mass is suspended from the torsion wire, like it's balanced on a beam. And you bring other big masses near it, like lead balls, and it deflects them. And so actually, it doesn't just deflect them, right? Because this is balanced so delicately, it causes them to like wobble. So it'll cause them to wobble around a new center, right? And then they'll come to rest around a new center. And using that, you can determine the gravitational constant. Yeah. That was Cavendish experiment. I mean, you'd have to be so precise and so delicate to get that to actually work, you know. And yeah, we did it in the lab actually. It was kind of fun actually. It involved lasers to track it. Yeah. So let's go back to our spreadsheet. Yeah, so I think using this information, we could calculate the gravitational acceleration on Earth itself. So going into LaTeX, let's get the Newton's law of gravity, basically. So everyone knows Newton's law of gravity. It's like the most famous equation ever. F equals G M1 M. So the little mass is like, the little m is like your mass, and then the big M is like the mass of the Earth over r squared. So 1 over r squared force. Here it is. That's it. Okay. So using this, we could plug in like the Earth's radius here. Oh, wait, no. Let's do another step of logic here. Let's plug in F equals ma over on the left. Like your mass times acceleration over on the left. And you can see like the m's cancel, right? And so you get the acceleration of gravity due to gravity actually doesn't depend on your mass. It's actually a kind of a strange phenomenon here. So this m, like your mass, it comes from momentum, right? Yeah, so here's acceleration of gravity is gm over r squared. But the weird thing is that these m's cancel, right? So the m used by momentum, right? That's like how hard you hit another object without like deflecting your speed. Like it comes from momentum. Is actually the same m that's used for gravity. So why is that? Why is the same m used in both equations, both momentum and gravity? And such that all objects orbit the same, right? It doesn't depend on their mass. They all orbit the same way. And that's actually a very weird and strange coincidence. And the way that we constructed our force equation was strange, right? Because F equals ma, I'll just type it up here. F equals ma actually, it's a bit bizarre because this formula forms the definition of force, but it's also the definition of acceleration. And it's even kind of the definition of mass, right? Kind of. But so this equation actually defines like two different quantities, force and acceleration. So it's a bit weird. Like, it's more like we set this up to like catalog forces as accelerations. It's like, this is how we're going to do it, you guys. We're going to catalog a quote-unquote force by an acceleration and weigh them by mass. Weight them by mass. So it's like, it's just a weird relation. So this is a very interesting equation, F equals ma. And I suspect that part of the sort of consequence of this, the weirdness of this equation is the fact that the m over here cancels with the m over here. It's just weird that that would happen, you know? Once you actually start thinking about it, like, that's actually kind of weird. And so it's almost like the actual law of gravity deals with acceleration, not force. Like, is gravity actually just an acceleration, not a force? Maybe like Einsteinian theory, like gravity is like the bending of space-time. So it causes an acceleration, not like a force of gravity. And so we can interpret it as a force by multiplying both sides by m. I don't know, it's just weird. Anyway, that's a little digression. Moving on from this. So we have g, we have m, and now let's plug in r for like the radius of the Earth. So let's call that like r naught, radius of the Earth, r0. Where is, oh, there it is. All right. So what is our force of gravity going to be at the radius of the Earth? So let's call that like F0 or A0. We want the acceleration, A0. Well, it's going to equal the mass of the Earth times the gravitational constant divided by, power 2. Yeah, using like these spreadsheet notations is interesting. Spreadsheets is a very, radius of the Earth is a very convenient way to solve certain engineering problems. So there it is. Oh, look, it's close. 9.7. Look at this. It's very close. 9.79897. So it actually should be like 9.81. So what did we mess up? Like, did we get the mass of the Earth a little bit low? Is the radius of the Earth just a little bit off? Or maybe like because our Earth is not a perfect circle, it's like a little bit ovular. Maybe that causes a little bit of a stronger force at the equator. So it's a little bit less. But yeah, we're within like a percent, you know, of the answer. Very close. Okay, so now let's determine the point where geostationary orbit is, right? So let's return to LaTeX. All right. So what is the speed that you orbit, right? Is going to be, well, the force dragging you down is going to be this. The acceleration of pointing down towards the Earth is going to be gm over r squared, right? So what do we know about the force of like an object that's going in a circle, right? The force inward is going to be v squared over r, right? And you can actually prove that. I could go through like the proof of that, but it's going to be v squared. Let's get rid of this. v squared over r. This is the acceleration of like centripetal acceleration, right? So it's your acceleration inwards towards the center if you're like going in a circle, you know. I'm motioning with my hands right now. I wish you could see. I'm like, I don't talk with my hands like that much, but you know, I do a little, especially when I'm like explaining math problems. I get like super animated. I start talking with my hands. Anyway, so we can set these equal to each other. Yeah. We could set like v squared over r equal to gravitational acceleration. And we could get and we could like solve for r. Well, no. No. So okay, here's what we want to do. We want to get v in terms of like arc, right? So if you're going a velocity v, how many degrees per second are you going through, right? Your arc per second, your angular velocity, in other words. So angular velocity is v equals, is it w over r? I don't want to be wrong. It's hard to think when you're like streaming angular velocity. Let's plug it in. It's always good to like look these up. Here it is. Yeah, so they use this omega symbol. Angular velocity. So it's like the degrees per second that you go through. Yeah, so v equals rw. V equals rw. So I guess the longer the radius, right? The less angles per second you need to... No. Yeah, the less angles per second you go through to get the same velocity. Yeah, so anyway, let's plug that in here. We can... Okay. V equals like RW. R omega. Yeah. There it is. Okay. V equals R omega over here on the right. And we could plug that in over here on the left. And of course, what are we going to get? Well, it's going to square. So we're going to get omega squared times R on the left. There it is. Then we could like, is it really going to be 1 over r cubed relation? So whenever you get a weird relation that you're not expecting, I would advise you just to take a moment to stop and just think, because that'll save you so much trouble. Like if you say, oh, well, is it really like 1 over cubed? That doesn't make sense. That's very important to think about, because you could be onto something. It's just a little bit of advice. Anyway, I'm going to go with, I think we're doing it right. I think we're doing it right. So we divide both sides by r. And we take the square root. And we get like omega equals square root of this side. This is like r cubed on the bottom. Yeah, so this is what it looks like. And of course we know W, right? Because we know we want geostationary orbit. So we want the point at which, wait a second. Okay, what are the units of angular velocity? What are the units? So this is called dimensional analysis. Dimensional analysis is when you look up the units of something to figure out like what it is or what it does. And you can actually like do algebra with the units in an equation to figure out if you're calculating the right quantities. I think I'm doing it right. Here we go. So let's look up the units. It should be like radians per second if we're doing it right. What is it? Oh, they're just reciprocal seconds. Interesting. Oh, no. SI unit of angular velocity is radians per second, yeah. So it is radians per second. So what is the radians per second of the Earth, right? It spins around a full 2 pi in 24 hours, right? So it's 2 pi divided by 3600, or how many seconds are there in a day? Well, it's 24 times 60 times 60. So we'll calculate whatever that is. I think it's like 84,000 or something. Can I bring up my calculator without it? Okay, here's what I'm gonna do. I'm gonna go to this room here, and then I'm gonna bring it up, just to be extra careful. Calculator. There we go. So it's 24 times 60 times 60. Number of seconds in a day. So it's 86,400. So actually, let's like plug that into our spreadsheet. Yeah, so seconds per day is this. And then we could get like angular velocity, right? Angular velocity of the Earth. Of Earth. I don't know. WE, right? This is the angular velocity of the Earth. We're going to use big E because it's the Earth. Equals 2 times pi divided by this. Uh-oh. Oh no. What am I? Oh, of course. I have this like W here instead of a 2. There it is. So this is the angular velocity of us right now standing on the Earth. Should be. Yeah, radians per second that we're like sweeping through as we spin around the Earth. So let's plug this in to our other equation. Let's go to this equation here. Oh wait, no. I solved this the wrong way. I gotta do algebra to solve for R, actually. So let's do our algebra the other way. So actually we're gonna get like a cubed root. Is that actually right? It doesn't sound right that you get like a cubed root out of this. Is that actually the way it goes? Well, let's just do it. The thing is, the algebra is smarter than you. Like, even if you think that you can, like, somehow the algebra knows more than you do sometimes, you know? Actually, I'm not sure how to do, like, a cubed root. Cubed, okay, 3. Actually, I'm going to look up, like, how to do a cubed root in LaTeX. Cubed root, LaTeX. Oh, interesting. Okay, that's an interesting notation. So what I'm going to do is I'm going to do square root, and I'm going to put like a little 3 here. And then I'll put it in there. So R equals square root of GM over omega squared. GM over omega squared. Does that look right? Look at there's a little 3 here for the cubed root. I mean, it's more, generally we don't like this root notation, right? This sort of like root notation is a little bit, it's a little bit uncomfortable. Generally we like doing things like to the power, you know? So like this. Left, right. To the 1/3. Look at that. It's just a little bit better notation, you know? I mean, you don't have to do it like this. I mean, everybody has. So in like math and physics, everyone has their own like notation, you know? And you can almost tell like who wrote this up based on the notation that they're using. Your notation is kind of like your own signature, you know? Everyone has their own unique signature. Everyone has their own unique notation that they like to use. So a lot of times people who don't sort of, they're not in the business, so to speak, they kind of get really linear with their notation, and they're like, you have to use this notation, you have to do it like this. No, everyone has their own like notation that they use, you know? A little bit free form. It's a little bit of expression that you can put into your work. Anyway, I'm a little bit worried by this 1/3 because I'm not sure that's I'm not 100% sure it should be a third. The math is telling me that it is, so trust the math. Trust the math. Believe in the math. The math will never lead us wrong. Unless we're doing it wrong. Yeah? Okay, so using this, we're gonna get we should get the radius of geostationary orbit, right? So let's plug in our quantities and then do this like to the 1/3. So where's our spreadsheet? Here. Let's go geostationary orbit. Or let's call it R sub G or something. Arb sub P, because I feel like it, equals power to the 1/3. Let's test it out. I'm actually not sure that works. Yeah, okay. So it's gonna be, what is it, G times M divided by omega squared. Omega squared. Okay. So is this it? Is this the right answer? Well, that's 42 million kilometers. That doesn't sound right. That doesn't sound, I thought it was 26,000 miles. So clearly something went wrong here. Clearly. Is this wrong? 2 times pi divided by the seconds in a day, so that's radians per second. Makes sense to me. Seconds in a day, is that wrong? 86,400. That's correct. G is correct. Mass of the Earth is correct. It's in kilograms. Is this actually giving me like the cubed root? Let's try like the cubed root of 27. It should be 3, right? Oh wait, what? Wait, no. This is leading me astray. This power function. Oh, 27. No, let's put 27 here. Yeah. So it is working properly. Then what went wrong here? What went wrong? Clearly there is an error. So let's do dimensional analysis. So when you get something wrong, let's do dimensional analysis. What are the units of G, right? So G is, I'll look this up. Gravitational constant. So G is newtons times meters squared divided by kilograms squared. OBS. Okay. So using dimensional analysis, we can go like G tilde. What is it? What did it say? So the big weakness that I have is I have a very weak memory. So I tend to forget things a lot. Newtons times meters squared divided by kilograms squared. Okay, newtons, meters squared divided by kilograms squared. So this is the units. Oh. Tilde. I want that tilde there. No. What is the control sequence to? Oh man, I'm actually gonna Google this. How do you do text in LaTeX? Text in LaTeX equation. Figuring this out. Oh, I should be doing it right. What am I doing wrong here? Dang it. Well, I could go like proportional. It sucks that I can't do it. It should be text. Oh, I might need to like import a new library. My internet right here is very weak. I'm actually surprised that I'm uploading. Oh, it's just text RM or yeah, text RM. There it is. Of this tilde thing. Oh, it doesn't want to show it. Oh man. I could do this. Nope, that looks bad. Look at this. No, text boldface. Let's try that. Well, you get the idea. I mean, it's just notation at the end of the day. Yeah, here we go. This is pretty good notation, right? So this is the dimensions for G is newtons meters squared divided by kilograms squared. Next, we'll do the units for M is kilograms. Kilograms. Is it really kilograms squared? Yeah, it is. Oh. So M is kilograms. This is radians per second squared. So omega is radians per second squared. No, it's just radians per second actually. All right. So now a newton is a kilogram meter per second squared. Let's put that in. A newton is a kilogram meter per second squared. Oh no, I believe it's meters squared per second squared, right? No. It's meters per second squared because it's mass times acceleration. Yeah. Yeah. So now we can use dimensional analysis to find our mistake, hopefully. There we go. So plug in newtons here. You're gonna get G. Yeah, G has the newtons meter squared per. Okay. So kilograms times meter cubed. Are you sure? No. Is that right? Is that right? So kilogram. So once you plug this in to G, it's going to be kilogram meter cubed per second squared. And over omega squared, it's going to cancel the second square. So our dimensional analysis doesn't work, right? Actually, let's plug it into an equation. So let's plug our dimensions into this equation, right? So R is going to be, well, the units for G kilogram, what am I doing? It's these. And then we're going to plug in the units for M. And then we're going to plug in the units for omega squared on the bottom. So, yeah, let's do it like this. Let's do like a fraction here. Okay. So, what cancels with what? So, we have... So this cancels with this down here. This is very... This is I can't... I need to, like, multiply these out. So, I have to go, like... See, fractions... You know, don't sleep on fractions. They're kind of useful sometimes. No, metric users like to like pretend that fractions are universally bad, but they're not. It can help you see things. So there we go. So yes, something went wrong with our dimensional analysis, right? Because this should be over kilogram squared, but it doesn't cancel completely with this up here. Right? So newtons is kilograms meters per... Yeah. There's something wrong here. Because this is supposed to calculate to meters. Because R is in meters over here. So yeah, what did we do wrong? Let's follow our algebra. So A is meters squared. Or no, meters squared per second squared divided by meters, so that's meters per second squared, is A. Yeah, okay. So that's correct. Up here, is this correct? G is, of course, this. Newtons, meters squared per kilogram squared. Once you plug in your newtons, it's going to be kilograms meters cubed. No. Kilograms meters cubed. No, meters cubed over kilogram per second squared. Kilogram second squared? Is that right? Is that right? No. No. Wait a second. Oh, no. It is right? Yeah. Because I know that this is the right formula, so G times M over R squared. Let's do that. So G, let's do G, let's plug in like N up here. So G equals, plugging in our newtons. 1 over kilogram. Kilogram meters squared meters cubed. No. I think I know the issue. What? No. Okay. I can't get lost here. I have to do the algebra correctly. Okay. G equals kilograms, meters cubed. No, meters cubed over kilograms per second squared? Is that really it? Yeah, meters cubed over kilograms per second squared. So this would be way, way, way easier if I could do it on paper. If I had like a stylus or whatever, this would be so easy. Yeah, it says it right here. Meters cubed divided by kilograms second squared. Meters cubed divided by kilograms second squared. These are the units for G. So if I plug G, meters cubed per kilogram per second squared, up here, I mean up here, then I multiply by M. That's going to cancel the kilograms on the bottom. And then I'll have meters cubed per second squared. So meters cubed per second squared. Divided by meters squared. So I'm going to have meters per second squared. Yeah, so the dimensional analysis works for both of these. And then when I set them equal to each other, here, I just do algebra for R, right? But I plug this in. So this is meters per second. And this is meters divided by seconds. Meters radians per second. So it should be the... This looks right. So where did I go wrong? So this all looks right. Just solve for R, right? You bring the R over here, the W down here. It looks right. And yet I'm getting the wrong answer out. Oh well. This is a bit embarrassing. I can't be getting wrong answers like this. Maybe the answer is in our spreadsheet. Times omega. Dang it, what am I doing wrong? Alright. Yeah. So now I'm getting a little bit nervous because I'm getting wrong answers out. G times M divided by, this is right. Actually, yeah, okay, so this is right. Actually, I'm wondering if I could get it in terms of this instead of in terms of G. Might be nice. So G times M divided by omega squared to the 1/3. Why is this the wrong answer? I'm gonna... Oh, I'm so dumb. Oh my god. Oh, no. Okay, no, I know the issue. So the issue is that it's in terms of meters. I was expecting it in terms of kilometers, right? I was like, oh, this is supposed to be in terms of kilometers. So I was like, 26,000 miles is not like 1,000,000 kilometers. Like, what am I... This is in terms of meters. Yeah. So you gotta divide by 1,000 equals this divided by 1,000. Yeah, there we go. 42,000 kilometers, which equals how many miles? What's like the mile to kilometer calculation? Isn't it like So a kilometer is 1,609. No, a mile is 1,609 meters. A kilometer is 1,000 meters. So it should be like 1,609. It should be like 1.609. Right. So we have to divide. So equals this divided by. Well, I could just put the ratio. 1609 divided by 1,000. Yeah, 26,000 miles. Oh man, it was right the whole time. Oh, I went into all that dimensional analysis. I was like, oh my god, I'm freaking out. What am I doing wrong? I'm like, oh my god, I'm gonna have to like hang up my hat. And the problem is, I suppose the problem is, it's hard to do dimensional analysis in a quick fashion when you're not using a pencil and paper, right? Because if you're using pencil and paper, you can just like write it out and then quickly cancel. But I'm using like this awkward latex method. I could have done it in GIMP, right? I could have like tried to write it out in GIMP. My handwriting is super bad though. Yeah, I blame my second grade teacher for my terrible handwriting. She was not teaching us the right method, definitely. So yeah, 26,000 miles. I can actually look up the exact value. So this is going to be like the exact value down here. I'm going to color it in a different color, like blue. So what is geostationary orbit? Yeah, 22,236 miles. 22,230. Is that right? 22,000. Why did I get 26,000? I thought it was 26,000 actually. This does not look right to me. 36,000 kilometers. Interesting. Yeah, 22,300 miles. Okay. So in that respect, there is a problem here. So think about it. So this, let's go to our, so is this error that we got over here, this like little error, is that enough to build up to this error here? I believe, is it? How could we figure that out? So this error here is going to be, let's go to latex again. Let's go to latex again. Yeah, so our acceleration is this over here. So I suppose a tiny deviation in A would be equivalent to an even smaller deviation in R, right? So yeah, because this is like a squared over here. So a very small deviation in R yields a bigger deviation in A. So I think our R, so I think that these values are very well calculated. I think that the mistake that we got in A is entirely due to R. Right? I think that's why. So we got a deviation of like, how many percent? Like a fraction of a percent in A, which should mean a deviation of less than that, like a square root of that in R. So I'm not seeing how we're getting the difference between 26,000 and 22,000. That's a big difference. So clearly something went wrong here. Seconds per day, 2 pi divided by that. Yeah. Radius. Oh, no. I know what it is. Yeah. So think about it. This is actually because, okay. So we didn't account for the radius of the Earth, right? Because the internet is giving us the answer as the height above above the Earth. So like the height above the Earth. And so in order to get that distance, we need to subtract the radius of the Earth. Right? So let's do this equals equals this minus the radius of the Earth. That is the radius of the Earth, right? Oh, let's calculate the radius of the Earth in miles. So how many meters per mile is it? 1609, right? Equals divided by 1609. So this should be this divided by this. Oh no. Minus this. What am I doing? Divided by equals this minus this. That definitely fails our dimensional analysis. Oh, there it is. See? Oh, yeah. And look how accurate it is, right? It's so accurate. It's like, because as I said, the variation that we got in A before, like this variation here, it should be 9.81, but it's 9.7. The variation in R would be like a square root of that. So if this is, how much is the variation actually? I'm going to go equals this divided by 9.81. Yeah, so it's of the order of equals 1 minus. It's of the order of 0.1%. Actually, let's do like 100 times to get the percent. Yeah, so it's of the order of 0.1%, and so that means the variation that we got in R should be like a square root of that. So let's actually do that. Let's do equals this power of this to the 1/2. Yeah. Oh yeah. Oh, I forgot, because it's less than 1. It's actually going to be bigger. Of course. But yeah, so our R must have been off by about like 0.3%, right? So it's not a this R that we got up here. See how it's like rounded off? See how we have like 3 digits here that are like rounded? So that must be what it is. Our R is a little bit weird. Anyway, yeah, we got it almost exactly. So that means because the error in R is so small, the error that we got here is pretty small too, because it's like the cubed root of that squared. So yeah, let's calculate the error here. Let's go like this. Oh, let's go like 100 times 1 minus this over this. Should give us our percentage error over here. Yeah, it's about the same. It's about the same order of magnitude. Actually, equals this like to the 3/2 to the power of this to the 3/2. Oh, negative, because this is negative. Abs of this. Oh, it's so it's the same order of magnitude as this. These errors are like the same size. Yeah, so actually accounting for error, like error in a scientific equation or in your experiment, right, is actually like the biggest part. So like it's easy enough to gather data and like fit the data to like an equation, right? That's easy enough. But calculating the error is pretty difficult actually. So you have to like go through your equation and like track the error. And I think there's like different methods that they use to do that. Like they use like standard Gaussian error and stuff like that. But anyway, this is just the basics. So we're calculating geostationary, the distance to geostationary orbit. So this is it in miles. It's like the height above the Earth. This is the distance from the radius in miles. So I should like label these. Just like add a new column. Insert column after. This is like and what is this? Oh yeah, this is like the kilometers. This is this is in meters. This is kilometers. This is miles from center. And this is height in miles. Like height above the surface. So next next we are this is a little bit sloppy, right? You don't want to have like your units on the left. Like it should be like your units are across the top. Whatever, it doesn't matter. Like spreadsheets are a little bit loose, right? You're just like messing around on spreadsheets, so it doesn't have to be super formulaic when you're dealing with a spreadsheet. Okay, so next, so we know the distance to geostationary orbit. So that's the distance from the Earth at which you're orbiting the same rate the Earth is turning. So you're like hanging above a single location on the Earth. So that's a very ideal location for like a spy satellite. It's like hanging in the air above a single location of the Earth. So our space elevator is going to be near there. And I say near there because let's do this. So let's say that this is like geostationary orbit. Let's do a new layer. Let's say that this is like geostationary orbit, right? Well, the rope itself, like the line itself, has some weight, right? So like let's say you have your spaceship here. I want an orange spaceship, so let's do that. So you have your spaceship here. Well, you still have to deal with all this mass dragging you down. So actually you're going to be a little bit above geostation. You're going to be like out here. And that extra like distance is just pulling up this rope. It's just pulling it up. So that your center of mass is here. Your like, center of mass of you, including this rope, is going to be here. But your spaceship won't be here. Like your space station will be just a little bit past. And this will have like a lot of mass here. So it's enough to like pull this all the way up. So it's like a stretch string. So actually when we're dealing with the failure of certain materials, like how high can you build? That's like an interesting question. When it comes to space elevators, we're dealing with the tensile strength of those materials, not like the compression strength, like when they collapse. So what is going to be, let's do some material science here. Like, let's say that we're building a tower and we're trying to get as high as possible. We're trying to get to geostationary orbit, 26,000 miles, 22,000 miles above the surface. That is huge. So we have to build 22,000 miles into the air. So how high can we generally build? Assuming that it's like a stretch, we're using the tensile strength. We're not going to use the compression strength. So one question would be like, how high can you build? And that would be using like the compression strength. But we're dealing with the space elevator, so we need like the tensile strength of these materials. So let's just use the tensile strength. So actually, I will show you here. Let's go to here. So these are like engineering values. So here's the graph. So the stress on an object versus the amount of deformation that the object experiences, right? So the object like twists a little bit, or it turns, or it stretches, or it compresses, and that causes a force. And that force is the stress, or I guess the stress is not a force. Stress is like what are the units of stress actually? See, we're doing dimensional analysis again. Yeah, stress is it PSI? Actually, I'm just gonna Google it. Hold on. Let me like hide this. I don't want like weird Google results to show up on stream. So stress. I should say like mechanical stress, because I'm getting lots of results for like migraine headaches. Got to be accurate on your Googling. So what are the units of stress? The units are pascals, yeah. So PSI. So stress is force per unit area. That's what a pascal is. Like you can do the dimensional analysis here. This is going to be newtons per meter squared over here. Yeah, so it's like a pressure almost. So if we go over here, we're trying to find the amount of force per unit area caused by amount of deformation of the material. And at a certain point, it fails, right? So it actually goes up linearly. It's like a linear approximation at first. And it reaches its maximum material strength, and it just fails. And it breaks. It fractures. And so the maximum amount that it can deform is the ultimate tensile strength. In reality, you don't want to be all the way up here, because this is causing permanent deformation to the material once you're past its like initial stretching. And so I believe this yield strength is sort of like a metric that they use to gauge pretty much the maximum. This is like pretty much the maximum strength. I guess this is technically the ultimate tensile strength is like technically the maximum, but for engineering purposes, you want, you know, the yield strength. So here is the yield strength for a whole bunch of materials. Here it is, ultimate tensile strength, yield strength for a whole bunch of materials. And here's their density, actually. This is very useful. So using these values, we can figure out how high we can build our space elevator. Can we really get to 26,000 miles? Or 22,000 above the surface? Can we really get that high? Let's find out. Returning to GIMP. So we have like a material, right? So we have like a material, and it has like, I mean, you could just think of it as like a rectangle or like a circle, but whatever. So it has a certain area that's like meters squared. It's like a certain meters squared. And then it has a force per area. So the force dragging it down is going to be like, if this is our building material, if this is our wire and we're building up into the sky with, this is going to be, gravity is going to be weighing each like slice down, right? So each like slice is going to be like weighed down. Like this is, if this is a differentiable small slice of material, it's going to feel a gravitational force downward. I'm just going to draw a slice. Each slice is going to have a force downward. So so like, let's say that we have a density function. Like, let's say that we could build different shapes. We could have like a pyramid shape. We could have like some kind of weird pillar shape. I don't know why you'd do something like this, but I mean, we could have any like density function. So density with respect to radius. So it'll be rho for r. Okay. But generally it's just going to be constant. Like for like in practical purposes, for like a wire, it's going to be constant density per radius. But let's think about it. So the amount of force on a slice of this shape is going to be, well, the total amount of force is going to be the amount of material that's there. So that'll be rho, I'm going to use P for rho, times rho of r times, well, the amount of mass that's there, right? Well, it's times dA times the cross-sectional area at that radius times dr, a differential thickness. And so this is like density. So this is like kilograms per meters cubed, and this is meters squared, and this is meters, or yeah, that works. So this will just be your mass that exists here, and so the amount of force that exists on that mass will be G times this. So this will be like M. So no. Remember, the force is going to be F equals G M over R squared. That's like the formula. And so then we could plug this in for m here. And then we do an integral for radius, right? So this is going to be plugged into here. And we'll have it in terms of dr. But the total force, I guess this would be like the force per height dr. Force per r dr. Whatever. Anyway, this is going to be an integral, because we're going to have to add up every single slice. So we have it for one slice, but we need it for every slice. So this is going to be like an integral from r0 to our final radius, what do we call it, rg or something. So we can like write this into LaTeX. You can see why LaTeX is so much better, because it actually like compiles it into a nice formula. So our net force, like weighing us down, is going to be equal to the integral from r naught to, let's just call it r final, like rf, and then of g m frac g over, this will be over r squared, and it'll be g, what is it, rho times a of r, cross-sectional area with respect to r, times dr, of course. So I believe it looks like this. Oh, times the mass of the Earth, of course. So the mass of the Earth is going to be like, let's just put it next to g. Oh, and rho is a function of r, of course. So in practice, so now in order to solve this integral, right? Do a big skip. Oh, let's just do like a new page, actually. Page break. Yeah. It's on the next page. Okay, so in order to solve this, we have to start making assumptions. So a of r, we're going to assume is a constant. We're just going to assume that it's a constant area as you build your pillar up. I mean, I guess we could experiment with different shapes, like a pyramid shape or a funnel shape, or I guess you could do that, but the thing is, I think that you can approximate any of those shapes as like a series of pillars, maybe. Maybe not. Maybe that doesn't work. I guess for tensile strength, you could do that maybe. Anyway, our rho of r, because we're dealing with a single material, we're not like involving a multiple materials. We just want to know for every single material what it's going to be. This is going to be a constant, right? Our material is the same all the way up. So it's going to look like, it's going to lose its dependence on r. These are just constants. Yeah. So now we just have an integral for r, 1 over r squared, which is, of course, you know, we all know what this is. I'm sure, right? Like, we all know, right? There's nobody in the audience who doesn't know this, right? Of course there is. It's fine. It's fine. Calculus is, you know, some people have trouble with it. The thing is, I initially had a lot of trouble with calculus, actually. But what I did was I just practiced the fundamentals over and over and over. I looked up like the definition of an integral, how we know an integral works, and I read through the proof for it like 10 times, and eventually I just got it. Eventually it became so routine to me that, I mean, calculus is just so easy for me now that anyway, it's going to be, the integral, of course, is going to be negative like 1 over r. It's going to be negative frac 1 over r. And you could get to that level too, you know. And that's what you need for like higher level subjects, like being an engineer, being a scientist, being just anything. You're gonna need like higher level math. Oh, and this is evaluated. So there is a little tricky thing that you can do to get an evaluation bar. I believe you go like left, right, and then you put a dot here. Is it here? And then you make this one like a line. Does this work? Yeah, so I have my evaluation bar, and I just go to like our final our initial. Yeah. Well, with LaTeX you can like play around with the formatting. So they make there's ways to do this better than this, but I don't want to look them up right now. just deal with it. Just deal with it, you guys. It's just formatting. This is gonna be like left, right. It's gonna be 1 over r final. 1 over. Oh wait, we gotta think about our signs. So the force is actually negative. It's actually like pointing towards. So the force is actually like a negative. It's pointing towards the center. So I actually screwed up a little bit here. So these should be negative up here. Yeah. So I screwed this up. These should have been negative. But, you know, you get the idea. And so this should be a positive here. Is this correct? Minus frac 1 over r sub 0. So let's think about our there. Let's think about this. So, let's get rid of my eval bar. Yeah. There we go. So, 1 over r naught is actually, because r naught is bigger, no, rf is bigger, this is going to be less than 1. This quantity here. So 1 over a smaller number minus 1 over a bigger number will be a negative number. And so our force will be negative, which is correct. It's pointing towards the center. So this is like the net force of our wire. It's like pulling us down. Let's see. I think I missed my area. Yeah, I gotta plug A in here. So. Yeah. So I got this big constant out front. And I got my. So I guess we should plug in like. So let's do this in terms of an arbitrary r. Let's do this in terms of like, and we could solve for r. Right. So let's say that our final r is not known, is like a value, and then let's solve for r. Well, let's not do that yet. So let's think about this. This is the amount of force that any like cross that you have to hold up, right? So like let's say that you have a whole wire below you. Let's say you have a hook on the top. This is a good way to think about it. GIMP. I'll do a new wipe away my mistakes. So let's say like here's the top of the wire or the pillar or whatever. And let's say we have like a hook here. So this would be like how much force this hook has to hold. right? Like how much this hook has to pull up. It'd be like that. But like how much the net force it's like pulling it down. The net force that's like pulling it down. Once you do that integral. But at a certain point, at a certain like height, it's gonna, the force per area is gonna be too much. It's gonna cause the material to collapse. It's gonna like cause the material to snap, I guess. So what we need to do is, let's go back to latex. What we need to do is plug in force per, hold on. I guess F over on the right is going to be force per area times area, right? Yeah. So this over on the right is going to be like, what is it? K? What is the symbol that they're using for stress? I believe it's like a kappa times area. This is like force per area times area. And then the areas cancel. Yeah. And so then we get the force on, so the amount of stress that this causes to like a cross-sectional piece of the rope. Right? Yeah, because this is units of PSI. So this is newtons per square meter, and this is in square meters. So this calculates to newtons, which is F. F is in newtons. Yeah. So then our A's cancel on both sides. And we just get, yeah. We just get this relation. And so that we can actually use this to find, like, if we know our maximum tensile strength, right? We can find the radius at which we reach this maximum tensile strength, like sort of the maximum height that you can build using this material. Knowing the density of the material, the mass of the Earth, the gravitational constant of the Earth. So now let's solve for R. Let's do it. So this is going to be kappa over GM rho. Will be like the characteristic constant that we're carrying around. Kappa over GM rho. And I guess we have to subtract 1 over R squared, or 1 over R naught. So bring these on the bottom, then add 1 over R naught. Oh yeah, okay, we got it. We got it. Equals, of course, equals 1 over R. Then we have to, like, you know, flip these. So it's just some algebra. So R equals, yeah, I'm like, I'm not going to give you too much information about my setup, you know, but let's just say that I have to reach around my microphone to type on my keyboard. So I'm like, typing is kind of awkward for me right now. So that's why I'm typing super slow. I'm not like, I promise you, I'm capable of typing much faster than this. And then, like, how you simplify your equation is kind of, if you don't simplify it, I messed that up. If you don't simplify it like the way that people like, they might get angry at you. They'll be like, you did it, like, why'd you do it that way? You know, you should have collected these terms over here, put this on the bottom here. Like, you failed us. So now I think what I want to do would be like multiplying the top and bottom by GM rho, right? And then multiplying one like R naught. So I just don't like the fraction within a fraction stuff. Like, it bothers me. You need an R naught out front times a constant GM rho. Oh, hold on. Hold on a second. No, never mind. I was thinking that rho had something to do with K, but it literally doesn't. No, I want to get this in terms of K over rho, actually. So I'm going to just collect my terms like this. Times R naught. GM times R naught out front. And then I will have a fraction here. Fraction. One over, what is it? Frac. Kappa over rho. So remember, kappa is my tensile strength, rho is my density. I want these like, yeah, I want these like collected together. Plus GM. Right? Something like that. So I'm going to have a constant out front. And then I'm going to have this constant here. And this is calculated for each material. So this looks good to me. This is like a good way to go, you know. Yeah. So using these values that we have from the website, right? We have these from the website. Let's calculate the maximum building height that we can get with each material. So let's plug these into our spreadsheet now. Okay. So this should equal, let's label it. Let's go like, scroll this way maybe. Oh no, I want to have like a whole list of materials. So these will be my materials. This will be the constant GM R naught. This will be my, I'll put it over here. Constant GM R naught. Actually, I'll just calculate that right now. Equals G times M times the radius of the Earth, R naught, which we know is a little bit off. Actually, we could get like a better value for this, but let's just move along. And then this is our constant out front. And then we need our other constant, which is GM. Is there really... Oh, wait, hold on. I'm forgetting something. No, this is... Hold on. No, I did my... Let's go back to the... I did my algebra a little bit wrong. It's okay, it happens, but you just have to catch the mistakes, actually. Yeah. So actually, fixing a mathematical problem that has like mistakes, like algebra mistakes, is kind of like finding the bugs in a program. Like if you're programming, it's kind of the same thing. Yeah. So I forgot to like put an R naught here. I'm actually gonna do it like this. I'm gonna let's go up to. Yeah. Let's get rid of this here. And let's put it like here. Frac. R sub 0. Like that. Does this look right? Let's do dimensional analysis on this. So kappa, this is, what is kappa? Kappa is force per area. So newtons per meter squared. This is meters cubed. So newtons per meter squared. And this is per meter cubed. So this is Newton meters. Newton meters. And this quantity, GM. Let's look at GM. Let's scroll up to our dimensional analysis. G times M. So it's going to be meters cubed per second squared. Because this kilograms cancels out. Meter cubed per second squared. GM. Meter cubed per second squared. And this is going to be, what do we, newtons per, newtons times meters. So a newton is a kilogram meter per second squared. So it looks like the second squared cancels out. The, I believe the kilograms cancel out. Meters cubed. I think that it works, right? Because this meter squared cancels with the meter cubed to produce meters. So I think that this is the correct formula. I was a little bit bothered because sometimes when you get formulas like this, the constant here is the same as the constant here. You know, you get that a lot actually. Well, maybe not a lot, but I've seen it numerous times. So I was a little bit bothered that there wasn't like a 1 over r naught here. It's fine. It just bothered me a little bit. Let's go back to our spreadsheet. So this will be our first constant, which will be GM over R naught. And then our second constant would just be GM. I guess we'll put this like A. Our constant out front is usually called A. Equals G times M. Okay. Constant A. Alright. Now. So now we need to get our... These will be the name of our materials. This will be the stress, or maximum, I guess, do we want yield strength or maximum failure strength? What was it called? Maximum tensile strength? Ultimate strength, yeah, ultimate strength. This will be yield strength. Ultimate strength, density, and this will be the ratio. Yeah, see, my big hands come into play. I have very big hands, so I keep hitting my trackpad and like dislodging my mouse. Yeah, big hands, people. You know, we're so discriminated against. Actually, we kind of are when it comes to like airports and stuff. Like flying on a plane is so miserable. You have no idea. Alright, let's go to our yield strengths actually. Yeah, I'll pull up the window. So let's start plugging these in. We have to keep in mind our units, right? So these are like megapascals. So this is like Pascal times 10 to the 6th, actually. And these are grams per centimeter cubed. They're not like, you know, kilograms per meter squared. So what is the conversion factor between grams per centimeter cubed and kilograms per meter squared? So I believe it's conversion factor M. Conversion. Conversion 1. What's a good name for straight, whatever, I'll just call this one Y and this one like P. I don't know. So the conversion between megapascals and pascals is just going to be 10 to the 6th. And the conversion between grams per centimeter cubed and meters per, or kilograms per meter squared. Well, I mean, you could work it out, but realistically, I could just like look it up. I guess you could work it out like. So I guess a gram is 1,000th of a kilogram. So you have to divide it by 1,000. Sorry, you have to multiply it by 1,000. So 7.8 grams per centimeter cubed is going to be like 1,000th of the kilogram. So you have to divide by 1,000 and then multiply by 100 cubed. So equals 100 power cubed divided by like 1,000. So it should just be 1,000, yeah. So let's go back to the spreadsheet. So I have just conversion factors here. Yeah. So I'm gonna use these to just correct our units, you know. So let's start with our first material. Our first material is structural steel. Call that like SS or structural steel. The yield strength equals 250 times. I guess this will be like straight from the page, right? This will be like me like reading rote from the page, and I'll have new columns here for like the corrected values. Corrected for this will be equals this times this. Actually, let's put them over here. So yield strength. I'll put like a little, just to indicate that it's been corrected for dimensions or for units, and I'll put ultimate tensile strength or ultimate stress or whatever. Ultimate strength, and this will be density. Okay, so this equals this times this. So on a spreadsheet you can make like static reference, or so to make a static reference to something, that means that you when you scroll, you don't this one doesn't scroll over here. You just put like dollar signs in front of it. So whatever. Equals this times this. I think there's like some shortcut to do it, but I just don't know the shortcut. And this one equals this times the same, which is 0 right now, and then this equals this column times 1,000. There we go. Okay, now we can start like plugging in values, and then our ratio is going to be equal to, what we want is K over, so we're going to have two ratios. I guess we'll do ultimate strength, actually, divided by density. Okay, so let's start plugging in values straight from the spreadsheet. So this will be 200, this will be 400, and this will be 7.8. So here's our ratio. And then over here, we should calculate our like ultimate build height, or like build height, which is going to be equal to this constant. Let's do static reference. Or no, it should be the one next to it. That constant A times divided by our ratio plus this constant here. I'll do static reference. Yeah. So this is like the ultimate build height. Actually, I want to calculate this not in terms of meters, but in terms of like miles. So I think that there's 1609 meters per mile. 1609. There we go. This is the ultimate build height that we can get with this material. So let's just make sure that the formula is correct. So it's going to be this constant here, which is, let's like widen this. GM R squared. It shouldn't be GM over R naught. Is that correct? GM over R naught. Yeah, it's correct. And then this constant is just GM. And I'm going to return to the formula one more time. Yep. So the GM is out front. The GM over R naught is added on the bottom. So GM over R naught is here. Our constant A is out front, yeah. And then this value ratio is just plugged into here. Makes sense to me. So I guess the maximum that we can get before it collapses, before it like collapses under its own weight with structural steel, is going to be about 4,000 miles actually, which seems like it's too high. Actually, that seems too high. You know, that's why I'm wondering if I'm doing this right. It seems too high to me. This is meters, right? R naught is meters. Yeah, it's meters. Okay. I guess our dimensional analysis works out. Yeah. So this should, in theory, generate a height in meters, which then we divide by 1609, because there's 1609 meters in a mile. Am I right about that? Am I off by like 1? I'm completely right. Yeah. This is like build height in miles, so I guess it doesn't get all the way to like geostationary orbit. But so it doesn't matter how, because remember we canceled out the areas, so it doesn't matter how like thin or thick this material is. You know, it doesn't matter if we make the material thicker. Now we have more weight to deal with, so it still collapses under its own weight. So this is irrespective of area, of like how thick we make the thing. So this is how high we can build. This is just how high we can get with this material. Now let's like plug in the next material. Now the spreadsheet should handle everything automatically. That's the nice thing about it, like spreadsheets. So I can just drag this down and start plugging in materials. So next on our list, we have mild steel. Let's not go through every single like variety of steel. Let's do titanium next. Titanium. $940, $1040, 4.50. 1040, 4.50. Okay. So this is the build height we can get. Let's make these like, let's change the formula and make these equal to, let's like round to it's like round to 1 decimal place. Yeah, because we don't need these extra decimals here. Yeah, let's just improvise it. So 3,000, a little bit shorter actually. Surprisingly, even though its yield strength is higher, its density is lower, so the ratio between ultimate strength and density is pretty much the same. Yeah. Alright, let's do... Oh man. Huh. Sorry, I got distracted. Let's do something else. Let's do like what is this called? Polyethylene or propylethylene. So they have a range from 12 to 43 for the yield strength. So I believe we want the high range, right? Oh god, okay. And some of these materials are like, you can't actually like build a structure out of them. But we could just plug them in anyway, you know. Like, can you actually build like a tower with propylethylene? It's probably not even like a structural material, you know. So let's use the high range. So it's saying 12 to 43. Yeah, I'll show you. Propylethylene. 12 to 43. So I'm going to use the high range, and I'm going to use the low range for the density, just to get like a maximum. So we're trying to find like the maximum theoretical limit here. Yeah, so 43 and 80. I'm surprised that there's so much of a difference between the yield strength and the ultimate stress. The graph that we looked at didn't look like there should be that much difference. I guess the graph that we looked at might have been like logarithmic or something. And it should be 0.91, so it's very light material. So we can get higher with this one. We can actually get to... Wait, what? Is this right? Oh no, that's just the ratio. Oh, no, it's about the same. It's about 3,000... This makes me suspicious that something's going wrong in our formula. The fact that these are all the same, it means that this constant here is very big, right? So like let's drop our density to, let's say our ratio is 0. What are we gonna get? Yeah, we're gonna get pretty much. No. Yeah, so we're gonna get much the same here, even if our ratio is 0. I guess, do we want a big ratio or a small ratio? Regardless. So if the ratio is 0, that means that it's like ultimate stress is 0. You can still build to... Oh! Wait, isn't that like the radius of the Earth? Did we forget to subtract the radius of the Earth? It is. Oh no. I knew something was wrong. Oh, dude. Yeah, so we got to subtract the radius of the Earth here, of course. What was I thinking? Oh, it's crazy how that... Oh, I'm screwing up here. Hold on. Okay, no, I'll subtract it right here. I'll subtract it in miles. I mean, I guess I shouldn't do that, right? I should subtract it in meters. Yeah. or in kilometers? No, meters. Wait, why do I have a -3 now? I should not have a negative number here. I guess it's just the inaccuracy of... No, because we know the build height is higher than a negative number. 3,961. How do we get a negative number there? Let me think. Wait a second. Hold on a second. I think we're missing a negative sign somewhere. I think we're missing a negative sign because... Okay, let's return to our formula. So this is how you do this sort of thing. It's like a process of figuring this out slowly. Let's return to our formula. So because this is a positive on the bottom, if we have a high ultimate stress and a low density, then this will be a very big number, which will make our radius smaller, which is not right. Our radius should be larger in that case, not smaller. So clearly something is amiss here. I think I missed a negative sign. So this is added. This is added. And it's 1 over... If I remember right, there was a negative sign on the bottom of this, because I've proven this before. Wasn't there? Where would I be missing a negative? So this calculates to a negative force. And then, I'm setting a negative force equal to like an absolute value. So actually, maybe I shouldn't do that up here, right? Wait, am I showing on screen? Yeah. So like, think about this. I'm setting, this force calculates to a negative. That means it's like a directional quantity. Like it's pointing down. But I'm setting this equal to like the absolute value of the force that is necessary to like keep the stress over here. So I think that this is an error. So I think I need a negative sign here to like balance out the negative here. I need to make this the absolute value. And then that carries through here, which we'll put a negative sign here, right? And I'll have a negative sign here and a negative sign here. I think that is the issue. Yeah. This is the issue. So I think when I set these two equal to each other, the right side here should be like the absolute value. So this should be like... How do you do the absolute? I guess you do like this sort of thing. Yeah. Yeah. Oh, I messed up. There. Like that? It looks like the absolute value, right? Anyway, so that means that we're gonna have to like correct for that, because this calculates to a negative because this is like smaller than this on the bottom. So we'll have a negative kappa over here, and then that carries down here, a negative fraction here, and then that carries down here. We have a negative fraction on the bottom, like that. So our final result at the bottom is actually going to be like this. Yeah. Yeah, like that. This actually makes more sense because now, yeah, this makes a lot more sense. It just does. So, because now when this is 0, this goes to r naught, or the radius of the Earth, which makes total sense. And furthermore, when you increase this value, right, we're getting a bigger ratio, so a bigger stress to density ratio. This increases r. So this definitely does make sense. That was this is the kind of error. So that wasn't like a dumb error. That was just an error, sort of in the math. That we have to like. So we have to like bug check our math. Whenever we come to a conclusion that looks like it doesn't make sense, we have to do this sort of thing. We have to like go back and make sure that it all checks out. And this is sort of the process of doing that. It does take a while, but you know, it's fine. It's fine. We want to get it right, you know. Let's get back to the spreadsheet. Let's plug in the correct formula to our spreadsheet, which should have a so minus the ratio instead. Yeah. Let's drag this down. Okay. Okay, so what if the ratio is 0? Then this should go to the Earth's radius. So yeah, I still have to subtract the Earth's radius here. So as I suspected, the height that you can build is actually much lower than miles. It's not going to be like thousands of miles. It's going to be like meters, you know. What did I mess up? Somehow plugged it in wrong. Minus this. Let's put brackets around it. Like that. Yeah. It's only 3 miles, so thought it would be much higher than that. Actually, it's so low that it's like suspiciously low. It's like, really? I'll round this. I want to be able to like round this to like 2 digits or just 1, like that. Yeah, so this is a lot bigger actually. I'm surprised that this material has such a much bigger ratio. I'm actually a little bit surprised by that. I guess it has a much higher yield strength and a lower density, so the ratio of yield strength over density just is much higher, yeah. So you can build like way higher with this material. It doesn't seem that the difference is huge though. The difference is like 1,000-fold. Shouldn't it only be like 10-fold? Really? The difference is... Okay, let's just confirm that this would be a 0. Yeah. So, actually, I'm going to do another column for build height in terms of meters. So, build height meters. I'll put like tilde in front of it. I'll just like widen the column so you can see it. And this will just be like the same thing, but without the 1609. This seems too big. Ultimate stress. Density is lower. is it really 1,000-fold increase in your build height? Does that seem right? It just doesn't seem right. Like, wow. Because if true, that is huge. It's still using the same like ratios over here, right? Yeah. What is going wrong here? Clearly something. Oh, yeah. I forgot this. So this needs to be like this. Yeah. I knew something was wrong. I was like, oh my god. I did something wrong. Yep, so we just caught another error. Yeah, so it's 15 miles. So because it's such a low number of miles, I want to like get meters too. Actually, let's just do like this sort of thing. And then we'll just do this equals this divided by 1609. Yeah. I'll round it, of course. I'll round to like 1 decimal place. Yeah. It should carry downward. There we go. Looks pretty good. So the build height for this one is 5.6 miles. Propylethylene. Let's go to the next material. So we should have all our ducks in a row now. Stainless steel, 520, 860, 8.19. 520 stainless steel. $860, 8.19. How high is it? Oh, 6.7 miles. So we're pretty far off the 22,000 that we need. just saying, you know, just a little bit far off, just a little bit. Let's go to I don't know, beryllium. 345, 448, 1.84. 148. What was it? Oh, my memory is so bad. Seriously, it's like a disability. That's how bad it is. 345, 448, 1.84. And then this is beryllium. Yeah. So how high can you build with beryllium? 15 miles. Pretty good, huh? Pretty good. Still not a space elevator. But yeah. Okay, good. I love how OBS doesn't show like pop-up windows and stuff. It kind of saved me there. Okay, what should we do next? Aluminum alloy, 414, 483. Aluminum alloy, aluminium, as the British say. $414. I mean, 415 is pretty much the same, but let's get it right. You know, we're good engineers here. We gotta get it right. Not really. And then this will be 2.8. So this time, oh, look at that, 11 miles. So how you can build with aluminum alloy. So I'm using the ultimate tensile strength to get like kind of like a theoretical maximum. In reality, we'd be using these values over here. These are like the actual engineering values. And in fact, you need like to be below this too. You need to be like significantly below this, or else your material will like stretch and deform over time. But we're using these values. These are like a theoretical maximum. So in reality over here, you can only build probably like 3 miles, not 11. But we're just like spitballing here, so we're going with 11. Okay, like let's go to what about copper? No, let's go to this like epoxy glass. No, the like densities don't look that good. This liquid metal alloy is interesting. Let's do that. Let's do this one. So liquid metal alloy. We got oh, I lost it. 1723, 1600. So for some reason the yield strength is actually higher than the ultimate strength for this one, which is interesting. I don't know why that would be the case. I guess it has something to do with it being like liquid. I don't know. I don't know why that would be the case. 1600. This is 6.1. How high can you build this time? 16.7 miles. Actually, let's get this a little bit more convenient. Let's like make these small. And we can just see it on the same screen. Yeah. Okay. What's next? What should we do next? You guys. Well, looks good. Strikes your fancy. I think maybe it's like polyester resin. No, because these don't have. So the reason why these don't have like ultimate strengths and densities, I don't think it wasn't tested for. I think it has to do with like the material itself. There's missing values on this chart. It kind of bothers me. I'm trying to like think of an explanation ex post facto. I'm like, well, they couldn't test for it because yeah, I don't actually know. So I just don't think that any of these are gonna work. Like brass, it's about the same as, it's even worse than like titanium. Marble, no. Human hair. But what's the density of a human hair? It doesn't have a density listed. What about spider silk? Oh, 1001.3. Let's try spider silk. How high can a spider web go? 1,001.3. 49 miles. 49 miles with spider silk? Are you kidding me? Wait, so spider silk builds higher than like, it builds higher than metal. I guess it's because you know, like the lower density, so it's not like collapsing itself. Amazing. Spider silk, man, it's the future. What else looks good? Like bone. Bone, no, these don't look like good values. We need something with a very, very high yield strength and a very, very low density. So what do we have here? This one, silicon monocrystalline. So it's like a silicon, like whatever, silicon mono. So it's what is it? 7,000 at 2.33. This is a really good ratio. So you can build 200 miles with this. 200. Look at that. That is crazy. But guess what? 200 is still lower than 22,000. It's an order of magnitude lower, actually. So we need another order of magnitude here. We need to like either decrease the density by 10 or increase the ultimate strength by 10. Okay. What's next? I'm gonna look for something with, okay, diamond. Let's do diamond. 2800, 3.5. 51 miles with diamond. That's how high you can build with diamond. And remember, this is the stretching. This is not the compression. So like this is how much you'd have to like stretch a diamond before it like shattered. Graphene. So now, here is kind of the upshot of this entire stream, or however you say it. This is like the summary of the entire stream. We need carbon nanotubes, because once we get into carbon nanotubes, look what happens. Okay, let's do graphene. So graphene is not like a rope. Like you can't like build a rope out of graphene. 13. How many zeros is that? 1, 2, 3, 4. 130,000. 130,000. One? The density is only 1. So yeah, this. So watch what happened. Look what happened here. This is interesting. We got a negative number here. What happened? What went wrong? Well, basically what happened is we passed infinity. So basically, like this ultimate build height, like how high you can build, eventually we get to a place where we can build infinitely high because of this ratio here. See this ratio here? When kappa over phi, or over rho, when kappa over rho equals gm over r naught, r goes to infinity. So actually there is a place where you can build infinitely high, where you don't even have to worry about materials collapsing anymore. And once we pass that point, this goes to like a negative number. So we've actually passed that point. So at this point, we can build infinitely high with this material. We've like reached escape velocity with this material. We've reached escape building height with this material. Yeah. So graphene works. It's good. It works. The problem is I'm pretty sure it's not like a rope. I think it's like a silicate like kind of thing. So I don't think you could build like a rope with it. And plus, like these are compounds that we can only create on very small micro levels. Right? So how much graphene can we really like assemble together into like a sheet? Like maybe like only a few atoms, you know, like 10 molecules or something. Now let's go to carbon nanotubes. So carbon nanotube ropes. No, these aren't good. So the first carbon nanotube ropes, carbon ropes. It's 3600 and 1.3. So this is actually isn't that good. You can only build 183 miles with this. But once we get into like the more advanced carbon nanotubes, like colossal carbon tube. This has such a low density. So this must be like that image that they often show of like a carbon nanotube where it's like a big giant like a circle with nothing in the middle. You know, it's like a tube. This must be that one because it's such a low density. So what is it? 7,000 at 0.1? 0.116. So you could build a really high with this. 111,000 miles? Wow. So this works. Carbon tubes work. Colossal carbon tubes work. What else do we have? Standard carbon nanotube. So this is like a real carbon nanotube. This isn't like some variation. This one's insane. 630,000 for the stress? Are you kidding me? This doesn't look right. Like, is this for real? 630,000 psi or whatever this unit is, and it's only 0.037 at the lowest. 0.037. Oh my god. This is yeah, this is huge. So this one, it works, but we haven't reached like escape velocity with it. We haven't like, there's still a build limit, right? But this one, oh my god, There's no build limit here. You can build infinitely tall with this, and it will never collapse. So basically, carbon nanotubes work. Like these carbon compounds, they work. Like we can build a space elevator out of these. It's just about assembling the materials in a long enough strands. So the issue that we're dealing with right now is that we can't assemble these materials into very large strands. We get them at like micro level strands, but we have to like join the ends of the strands together to create long strands. And if we could get long strands, like miles in length, then all bets are off. We could have a space elevator like overnight. Overnight. No, not overnight, but we'd also get so much more stuff, like new military weapons. We get like nano-sized like robots because these materials are so strong. We get like infinitely strong bulletproof vests. We get like what else? Like who knows? Who even knows what we get, you know? Like way better cutting material maybe, because these are like have so much tensile strength that you could like use them to cut things maybe. Like these would just change the world. These carbon things. So I've actually talked to like engineers who are like working on this stuff, and they're trying to use like various mills and stuff. Like they have various like one of the ways that you can do is you can like push the material through a perforated sheet and into like a broth, right? And then allow the atoms floating in the broth to attach to the end. And you can use that to successively attach strands, and until you spin a rope out of it. And so that's what they do with like other things. But it doesn't work with this material. Like it's too delicate, it's too fine. You need you need like the entire circle to be bonded to the entire circle. You can't have like a tangential bond. So realistically, like how do we do this? Everyone's working on this. Like everyone is working on this. Like this would just change. This would change everything. This and superconductors, really. Like those two big advances would just change our entire world. And this would enable us to a space elevator. You wouldn't need a rocket to get into space, right? You could just ride up the elevator, and now you're in space. And it saves so much energy. It saves, like we could just. It would be like so most of the energy of a rocket, right, is involved in getting from the Earth to low Earth orbit. Because that's when the gravity is strongest. We have to deal with all the air friction. So you need a rocket with multiple stages, and you need even more fuel because your stages have to be so big. So it's like the weight of the rocket increases, which means you need more weight, which means you need more weight, which means you need more weight. And so with this, you don't need any of that. You can just ride up the elevator. It's so much more energy efficient. It's just, and it's so much quicker too. Like you could just zoom up and down the elevator, and you could transport large amounts of materials up and down the elevator. So this is what you need for like an asteroid mine, right? You'd go up the elevator, get in your rocket ship, and you wouldn't need that much fuel because, you know, we got past low Earth orbit, so we don't need any fuel. And then we could just zoom out to the asteroid belt, bring back some asteroids, mine them, and then bring them down the elevator. And it's trillions of dollars worth of material. This is what we need. This is what we need. And the frustrating thing is that it's such a small, delicate little issue where it's literally just about like getting the milling process right, or getting the lathe process. I don't know what engineers do. I'm not much of an engineer. Yeah, but you know, getting the process right on the micro level would enable us to do so much stuff on the macro level. And you know, they're all working on it right now. They're all working on it. And if they make the breakthrough, you know, it's going to change everything. So one day we'll have it. One day we'll have a space elevator. We just need this. We just need this to work. It already works on the micro level. We need it to work on the macro level. We need to attach the strands together. And yeah. And I can't wait till we get a space elevator. One sort of consequence of the space elevator is like political. I mean, I don't go into politics on this stream, obviously, but consider that like the space elevator needs to be, where does it need to be? let's fill this with blue. It needs to be near the equator. So like land near the equator and like countries near the equator suddenly have like a big advantage. Like whoever can possess land near the equator has access to a space elevator. And it's like, oh, that's like really, really valuable. So countries like maybe in like South America or Africa, or I think Australia is going to come out really good because they're like pretty close, you know, like just south of it, like down here. Or maybe we'll just build like a big floating platform in the middle of the Pacific for this, with foundations that go all the way down to the bottom of the Pacific. That way it's like an international thing. It's like no one country owns it, you know. And it would suck if there was like 10 of them. It would be better if there was only like 1 or 2. Like maybe one on the opposite side just for like balancing purposes. Yeah. You have 1 or 2. If you had like hundreds of them, like, I mean, come on, like, that sucks so much. Nobody wants to look up in the sky every day and see that. So, I mean, this would be visible from so far away. Like someone like halfway around the world would be able to look up in the sky and see it because it eclipses the horizon, no matter how far away you are. I wonder what it would actually like look like, you know? It's difficult to know. Difficult to know. But yeah, I guess you could have it like a little bit off the equator, like up here. But in that case, it would still be coming out tangentially. So like if this is the ground, right? It would be coming out of the ground like that. It would be like leading over. And so people down here would be like looking up like, this is kind of scary. Like, what if this thing snaps? Like, actually, consider this. Like, where would it snap? Like you have your space elevator. Here's ground level. Here's the top. Where does it snap first? Here's like your space station. Does it snap first here or here? Or somewhere in the middle? Where is the... So I guess the greatest tensile strength, right? The greatest, like, force... Well, I guess, isn't it going to be near the top? Because the top has to lift all of this stuff, right? It has to, like, lift it all up. But the tension is distributed throughout the entire... Because it's like a rope, right? So if you pull on the string, the tension is distributed equally throughout the entire thing. Then again, this stuff up here is moving faster. It's like being swung around faster, right? By the earth. So if you're like holding a bucket and swinging it around, like this is a bucket filled with material, and you're swinging it around because you're crazy. You're swinging it around in a circle around yourself. This part of the rope is moving faster than this part of the rope. But I think the tension distributes itself through the rope equally, right? I just think it does that, right? So, yeah, because like the force in your hands here is going to be the same as the force in the bucket here. So it definitely distributes the force equally. So I guess there's no way to know where it would snap. Would it snap near the bottom maybe? I guess the bottom has like more atmospheric disturbances, right? But the top is getting hit by micrometeorites. Got meteorites hitting here, so. But the bottom has like atmospheric, you know, like blowing it side to side. So where would it snap? I guess if it snapped like, imagine if it snapped like here, and this whole like thing just fell, because it's long. Remember, it's like 26,000 miles. That's bigger than the circumference of the Earth, right? It's like 22,000 miles. Circumference of Earth. 24,000 miles, 25,000 miles. So it's almost as long as the circumference of the Earth. So if it snapped like here, this whole thing would fall, and it would crush like I don't know how thick it's gonna be, but it would crush stuff. Like it would just, I mean, it wouldn't like burn up in the atmosphere either, because it would like collapse, right? It'd be like a a slower collapse. So yeah, that would be like devastating. So in order to get to this like supremely high level of technology, we need better organization. Like we can't have like engineering mess ups. We can't have like a building that's designed wrong, or we can't afford to make mistakes. We have to get it right, you know? And so that requires a level of advancement that's maybe beyond our current civilization. I don't know. I mean, I hope not. We just got to get the right people in there, you know? We can't play around. Like, this isn't a joke. Like, this is like the future of our civilization. Like, will we be able to establish a space elevator or not? Like, the future of our entire species depends on that. So we can't, it's not a joke. Like, we can't play around with it. We can't like play, oh, like I like this person, so they're gonna get the job because we can't do that sort of thing, you know? It's gotta be, you know, we gotta get a good team together. We gotta organize as humans and get this done, you know? Get this done. So it's a big deal. Big project. It's exciting, but it's also disappointing that we haven't done it yet, you know? You'd think that we would have done it by now. Maybe someday. I mean, we're getting like advancements in AI, but I mean, the AI advancements are just like scary. They're like a control grid, you know? They're trying to control us with AI. It's not like liberating us, you know? It's not like advancing us to the next level of space travel and opening up new horizons. It's more like you get more control, you know? Yeah. I guess, remember when I talked about like introspection versus atrospection in my second chatting stream? I think that's a great stream, by the way. AI would be more like introspection, and this is definitely like atrospection. This is like we're leaving the planet to experience what's outside of the boundaries. Whereas introspection is like we're diving into our own mind and we're building worlds that satisfy our own mind. And that's like what the advancements in AI are doing. But we need to get this stuff going. We need to get like... So I guess rockets are fine. Like they're working on developing rockets. All this money is going into rockets. Trying to get like stuff on Mars and... But it's kind of futile, isn't it? Like we're spending so much money and energy on that when really we just need a space elevator. This is where the advancement is going to happen. Like this is what's going to solve the problem. Like I don't think rockets are ever going to be like a long-term solution, you know, to the problem of getting materials up and down out of the earth. Like we need this. Then again, like you have to consider like, is this even possible? Like a wire 22,000 miles in length, you know? Is that even like possible? Like feasible? Like even if you could build that high, you had the material, like would it be feasible? I mean, I think it would be. I think we're gonna do it, but we need to work harder on that. Yeah. Oh well. I had lots of fun doing this. I guess we could like close up the stream. Why did I scribble all over the earth? I used to draw like drawings of asteroids hitting the earth and like giant explosions. Like I'd draw like an asteroid here and like a giant explosion here. Yeah. I don't know. Alright. Let's close it up. I was streaming for much longer than normal today, so... Yeah, almost 2.5 hours, wow. I didn't realize it would take so long. I guess most of the time was like bug checking my math. Yeah, so these like rambles, these like chatting rambles are less... The information in them will be less accurate. Like I'm going to be making mistakes. I'm going to be making errors and, you know, messing up a little bit. Like my last, my one on the heavy side function, right? That one had errors in it. Like I was calling like a surface integral, a volume integral. And I was making errors like that, and it's bothersome. Like, I don't like having. I mean, I guess I have to accept it, because if I'm gonna be doing like chatting rambles, I'm gonna be making errors like that. It's just what's gonna happen. But I can make notes of it. I could be like, oh well, this isn't exactly right. I could put that in the comments or something. But the information in like tutorials, I'm gonna be making tutorials. Like, I made the trigonometry tutorial. Should be 100% accurate every time. Yeah. Anyway, this is like the process of working through a problem, like a real physics problem. This is the process. You're gonna make mistakes. You're gonna have to check your dimensional analysis to make sure that you got your units right. You're gonna have to, you're gonna have sign errors, right? You like miss a negative sign. You have to go back and find out where you missed that. You're gonna have to think very carefully about like, magnitudes. Like, wait, that seems too big. Maybe I made a mistake there. I have to go back and check that. You know, you have to go back and check things, and this is the process. This is like a window into the process of doing this. And yeah, this is what it's all about. So, all right. Well, I'm gonna go. I'm a little bit disappointed that I made some mistakes in the math and had to go back and check them, but I mean, it's fine. I think it's a little bit instructional, you know, giving people a little insight into how this stuff actually works. So I'm gonna go. I need like a catchphrase besides like heavy side out. I need like a eat your vegetables, kids, or I need like do your homework, kids. Okay. I guess I'll say something like walk fast, or no, like work hard, walk fast, and don't get sucked into the great abyss. Heavy side out.